what we're going to discuss in this talk are a number of questions which fall into a larger area, which I don't obviously not able to give a complete picture of, but in the larger area involving the study of geometry, topology, and also differential equations, analysis on what are called manifolds. So the plan for the talk is that there'll be three main parts, and these parts will be connected to three different number systems. There'll be a 19th century story, which will involve the complex numbers and what are called Riemann surfaces. And then there'll be a 20th century story, which will take up the bulk of our time, which will put this, introduce this in terms of another less familiar number system, what's called the quaternions, and talk about the geometry of a particular class of what are called K3 manifolds. Then the last part, what I call the 21st century story, in that it largely lies in front of us, will be related to an even more bizarre number system called the Octonions, and another class of these manifolds with the property of what's called special holonomy. So, of course, these dates, 19th, 20th, 21st century, are rather approximate. I'm not saying that, for example, everything about Riemann surfaces was done in the 19th century, far from it, but perhaps give some kind of idea. I'm certainly not saying that the most important thing in mathematics in the 20th century was these quaternions. That will give the wrong idea. I'm just tracing out this particular line of developments which can be fit into this theme. So the reason for choosing this range of topics comes largely from the last part. Dotted around in the audience are various scientists and mathematicians and physicists who are part of what's called the Simons collaboration on this special holonomy, working on developing this particular topic, which, as I say, to a large extent, the developments lie in the future rather than the past. So this talk is, to a high extent, my sort of attempt to explain this endeavor involving this study of this particular research area to a more general audience, but we actually will spend rather little time talking directly about this more advanced thing, and most of the time talking about these older and better established stories, but I hope will give the flavor of the whole area. So that's the plan. We need some preliminaries. So first of all, I need to recall to you or explain to you what are these manifolds, which will be the stage for all of the interesting geometry and analysis and differential equations that we want to discuss. So an n-dimensional manifold, it's a set whose points locally in small regions can be identified with coordinate systems, i.e. sets of n real numbers. So what one says is that the manifold is covered, it's containing a collection of charts, and these charts make up what we call an atlas. And that terminology is not accidental, but it's a very familiar example of this setup, because it's exactly what we do when studying the surface of the Earth. We take a crude picture of the surface of the Earth, if we're working in a sort of relatively small region of the Earth's surface, we have a chart with some coordinates. But if we take coordinates in some parts, say the green coordinates, and try to extend them a very long way, say into the region where we have the red coordinates, then there'll inevitably be some large extent of distortion. We cannot have very good coordinates that cover large parts of the Earth's surface, and we can't have any coordinate at all that covers the whole of the Earth's surface. You always have to miss out some point. So we need at least two charts to cover the whole of the Earth's surface. So a manifold is just a generalization of this idea, but we could have some more complicated kind of set. But if we stay in a small region on the manifold, then we just describe points by a collection of real numbers, by coordinates. But we should say, well, these coordinates are not unique, just as there are different choices of coordinates on the Earth's surface that one can take, different kinds of projections that have their own advantages. We're not saying that there's a particularly distinguished kind of local coordinates, just that there are some. So there are lots of things that we would want to define carefully if we were being more systematic, but of course we don't have time for that. So the only thing we want to mention is that there's a notion of a tangent vector at a point of a manifold. So these are, if you like, we have a notion of a smooth path in a manifold, therefore we should have a notion of the velocity vector of a point moving along that path, and that's exactly what these tangent vectors are. So these manifolds are ubiquitous in mathematics, in all kinds of different sets that arise naturally in mathematics or applications have this property that they can be described locally by coordinates. We won't take time out to give a large number of examples of this. Later in the talk, we will see various examples of interesting manifolds. But I should say, while they're ubiquitous, and with hindsight, the notion is a very obvious, a natural one, it took many years for this notion to really become crystallized in mathematics and formalized. So what we're going to do in the first part of this story is to look at one of the main ways in which this notion of a manifold entered, as it were, into mainstream mathematics, make contact with things that you would definitely recognize as mathematics. So this is our, and I've got my timing right, this is our 19th century story, part one. So let's go back to think about integration. We know that when we study calculus, we learn how to integrate various functions. This is one that we can integrate, right? This 1 over the square root of 1 minus x squared. The indefinite integral is cos to the minus 1 of x. And of course we see the cosine function appearing. The whole theory of these kind of integrals is bound up with the geometry of the circle. That's to say, solutions of the equation given by the equation in coordinates x squared plus y squared equals 1. The connection with this formula is that if x squared plus y squared equals 1, then y is plus or minus the square root of 1 minus x squared, which is just the term appearing in the denominator of our formula. And so make an obvious remark. Look at the circle. You see there are two over the interval, as x runs from -1 to 1, not including the endpoints, then there are two distinct choices of points on the circle, two distinct choices of this square root. You're making up what we might call two branches of the circle, and then these come together at the special points plus or minus 1, where 1 minus x squared is 0. So that's familiar, probably, calculus, but it's obvious to ask what happens if we tried other similar-looking formulae. What happens if we try to integrate 1 over the square root of 1 minus x to the 4th? Could we do that? Maybe there's some cunning substitution or trick which can write this in terms of standard elementary functions. If we draw the corresponding curve in the plane, so it's now given by the equation x to the 4th plus y squared is 1, we get a similar picture, just the circle has got a bit sort of squashed and distorted, but nothing looks radically different. So this is where the complex numbers come in. This was sort of a big, exciting realization in the 19th century that if we go to complex numbers, then the picture becomes much easier to understand. So rather than taking this equation x to the 4th plus y squared is 1 with real numbers, x and y, we let x and y be complex numbers. So we have a solution set, S, which will be a manifold, in fact, which is contained in the set of pairs of complex numbers, x, y, which is, if you split the complex numbers up into real and imaginary parts, we can think of that as 4 copies of R for R4. So inside this R4, we have this, in fact, two-dimensional manifold defined by the solutions of this equation. So now, the same, of course, we're not so used to thinking about something sitting in 4 dimensions as we were to drawing the curve in the plane. But we can try to do that, and the same general ideas apply. We look at the branch points, which are the equations of where x to the 4th is equal to 1. So now there are 4 of those in the complex numbers. X is plus or minus 1, or plus or minus I. And then, so away from these branch points, we have 2 different solutions of our equation, y, for each possible value of x. So, in fact, we can construct this surface S topologically by taking 2 copies of the complex numbers, the complex plane, and then making some cuts between the branch points, and then gluing together these 2 copies in an appropriate way. That's a bit hard to visualize if you're not a 4-dimensional being, gluing or sewing them together. So the picture, if you ponder this, looks like so. We have our branch points, 1i, minus 1 and minus I. We choose arbitrarily, divide those into pairs, take cuts between the pairs, take 2 copies of that, and then sew together the 2 copies along those cuts in an appropriate way. But topologically, it just looks like the picture at the bottom. We have 2 planes with holes in them, and then we glue the holes together to get something different. Whereas if we applied the same discussion to our original example, where x squared plus y squared is 1, then things would look topologically different because we'd only have 1 of these holes and we glue together, so we'd have this picture rather than this picture. So the surfaces would have different topologies. They couldn't be deformed one into the other one. So this is what, these sort of considerations, what shows that the idea of topology and manifolds are fundamental when one's studying very obvious natural questions of calculus. So in fact, more technically, it's often convenient to add points at infinity to our copies of the complex numbers. So if we just took the complex numbers themselves, we'd add a point to infinity and get a sphere, sometimes called the Riemann sphere. If we add points at infinity in the discussions we had before, then the pictures would look like this. So in one case, the thing we would make actually would be a sphere. In the other case, it will be topologically a torus. So it's this difference of topology which really shows that we couldn't just treat this integral that I call I of x just by, in some clever way, using standard elementary functions, that it really involves completely different kinds of objects. And this is just the start of the theory of these Riemann surfaces that we mentioned. And one of the important things in that theory, which I'll want to come back to, are what are called the periods of a Riemann surface, which are suitable definite integrals. So in the case we considered before, they'd be given by the integral from between the branch points -1 and 1, for example, or 1 and I, and we'll stick a factor of 2 in, for a reason you'll see in a moment. So these things correspond to integrating around closed paths on our Riemann surface, as in the picture here. So in our complex plane, we take these paths of integration, a green one and a red one, say, but when we think of it in terms of our Riemann surface, then there are two copies of two intervals, as it were, lying over, say, the red one, and then those stick together to form a closed curve inside our Riemann surface. That's why we put the factor of 2 in, because actually we'll double the contribution to the integral when we take both paths. So in terms of the Riemann surface, these periods correspond to doing certain integrals around loops, closed loops in the Riemann surface. Now, before getting going with the next part, let's just build up some more background to talk about the various structures on manifolds that one might be interested in. So a Riemann surface, for example, has the property that we can multiply the tangent vectors by complex numbers. That from the way we just defined them, everything involved complex numbers. So we make this intrinsic way of multiplying tangent vectors by complex numbers, or you just think of rotating them through 90 degrees. So that's one kind of a structure. Another kind of structure we want to talk about is a Riemannian structure, which is given by giving an inner product or dot product on the tangent vectors at each point. So just like we can take the inner product of two vectors in R3, on a manifold with a Riemannian structure, we can take the inner product. We have a way of taking the inner product of any tangent vectors. In particular, taking the square root of the inner product of a vector v with itself gives a notion of the length of the tangent vector. So these Riemannian structures are perhaps the most studied thing in differential geometry on manifolds, and a variant of this notion in which we allow inner products which are called Lorentzian signature is the structure on space-time which is considered in the theory of general relativity. So that's these are a fundamental notion, obviously, in physics. One of the important theorems about Riemann surfaces, proved around about the end of the 19th century, is that any Riemann surface has a compatible Riemannian structure which satisfies the analog of Einstein's equations in relativity. So giving a Riemann surface, you have a way of rotating vectors through 90 degrees, or more generally, you have a way of measuring the angle between vectors, but you don't have a notion of you don't completely have an inner product. You don't know what the lengths of vectors are. So there's one extra piece of information at each point to fix by giving the scale. That becomes a function on the surface. So the theorem says that there's a unique way to choose this function on a Riemann surface to satisfy the analog of Einstein's equations, where certainly that brings in what's called the cosmological constant. There's a real parameter one can introduce in Einstein's equation. So this is one of the sort of triumphs of 19th century mathematics, the proof of this theorem. It's normally discussed in a slightly different way. It's called the uniformization theorem, presented in a slightly different language. Another development we could sort of mention briefly, although we don't, so off the main line of our talk, is involves the study of the solutions of Einstein's equation on three-dimensional manifolds, which was developed very extensively over the last century, in particular in the work of Perelman, is proving a famous result with solving what's called the Poincaré conjecture. But these kind of results, proving the existence of certain structures which satisfy the appropriate conditions, what they amount to is solving nonlinear partial differential equations on manifolds. That's fine. So I want to talk a bit about that, but I'm going to do that largely through analogy. The model differential equation I want to consider is what's called the minimal surface equation. So that's a little bit different technically from what we were considering before, but has the advantage that one has some sort of intuition about the equation and the solutions, and the same main points apply here as to the other kinds of equations we're going to consider. So this has the advantage we can actually write down some partial differential equations. So here we are. So this minimal surface equation, the problem is that we take some given curve, closed curve in the plane, we seek a surface among all the surfaces which span that curve, we seek one which minimizes the area. So we can represent a surface, at least locally, as the graph of a function, u of two variables x1 and x2, and the solution of this minimization problem, or variational problem, always satisfies what's called the Euler-Lagrange equation, which in this case is that nonlinear partial differential equation written down in the middle of the slide. So it's absolutely unimportant that you know that. This is a differential equation and it has a natural geometric meaning. The other things we're going to talk about, there will be similar kinds of even more complicated differential equations lurking, but we're not going to actually write them down or say any more about them. But you just imagine that there are even more monstrous things than that going on. But one point to make is that if we consider things that are close to being a plane, so if u is small, then to a good approximation, we can ignore the quadratic terms, or more formally, we can look at the corresponding linearized equation, and that becomes something very simple, which I've written down wrongly. I see. No, sorry, no, sorry, I haven't. No, it's at the bottom. If we get what's called the Laplace equation for the function u, just that the sum of the second derivative in the x1 direction and the second derivative in the x2 direction is 0. So this is that's the most important among classical linear equations, appears everywhere in mathematics and mathematical physics. And one can learn a lot about these minimal surfaces from looking at this linear approximation. And that, as I say, that same principle applies very generally in the study of these nonlinear PDE. So I want to think about some kind of strategies that one might apply to solve this kind of problem. You know, our mathematical problem is, can we prove the existence of a surface spanning our given curve with minimizes the area? And this is a famous mathematical problem. It's not exactly in the class we want to consider, but it's a good thing to think about. And I say these kind of strategies, it doesn't really matter what particular equation we're talking about, because the same kind of considerations apply very generally to many different problems. So one thing we could do would be use method what's called minimizing sequences. We take, there's certainly some infimum of the possible areas of surfaces. We take a sequence of surfaces whose area is going down to that infimum. What we'd like to do is to prove that somehow that sequence converges, or we can choose it to converge, and then the limit actually will be the desired minima. So that's the kind of thing you have to do. Why should choosing this set of surfaces, where all you really know about their area, why should we be able to choose some sequence that converges? Another thing one might try is what's called evolution by mean curvature, or mean curvature flow. I think I forgot to say, it was written down, but I forgot to say it. This equation geometrically expresses the vanishing of what's called the mean curvature of the surface. The surface might be curving a certain amount in one direction, a certain amount in the other direction. You take the average of those to get the mean curvature. And that's geometrically what this formula is. So for any surface, it has a mean curvature. Then you can say we're going to evolve it by moving at a speed given by the mean curvature. And the hope will be that you would evolve into something where the mean curvature is 0. So this is another kind of much studied strategy in these sort of problems. Another strategy is what's called the continuity method. Certainly we know for some curves, we know we can solve the problem. For example, we might just take a curve in the plane, and then join our given curve to this known curve by some path, and show that we can keep deforming the solution along this path to eventually solve the problem we started with. But there we have the same kind of difficulty. What happens if we keep deforming along and then suddenly it develops some horrible kind of singularity and we can't go any further? Well, another approach, which actually be the one most relevant for today, is might call gluing some known solutions. And so this is something that will apply in the presence of a suitable parameter. So let's say a bit more about this. So this is what's called the bridge principle in the study of minimal surfaces. So we took two known solutions, two minimal surfaces, and then we consider joining their boundaries by a very thin bridge, as shown. I should have made it a bit thinner in the picture, like that. And then you can, the results of the kind can be proved, you can prove that there exists a solution for this bridged surface, which is made up essentially of taking the solutions that you started with and joining them by something flat along the bridge. Of course, the solutions for the bridge surface is not going to be exactly equal to the given one. When you introduce this bridge, even everywhere you're going to change things slightly, but it's going to be more and more equal as the parameter, which is the width of the bridge, goes to 0. So the way you would prove something like this is that you write down something by, you take your ingredients, your given solutions, the thing you get from the bridge, you sort of glue those, paste those together in as smooth a fashion as you can think of. You won't be able to write down a solution of the equations, but you'll get something that's very close to a solution, and then you aim to show that you can slightly deform it, which will involve typically studying the linearized equation to get a genuine solution. So this is another kind of technique that can be applied very generally to many problems. This minimal surface one is a good one for illustrative purposes. So now we finally come to the second part, our 20th century story, which you recall was involving things called K3 manifolds and quaternions. Actually, these things are normally called K3 surfaces, but that would be a bit confusing, so I'm calling them K3 manifolds for the purposes of this talk. But first, we should talk about quaternions. This is a four-dimensional number system discovered by Hamilton in the middle of the 19th century. So they're generated by the identity and three other objects, I, j, and k, with these famous multiplication rules, I squared, j squared. Oh, here I have gone wrong. I squared is equal to j squared. That's a mistake. Equal to k squared is minus 1. And then ij is k, but they anti-commute, so that's minus ji, and so forth. The rule for multiplicating ij and k involves cyclic permutations of ij and k. So ij is k, kj is I, ki is j, if I got it right. In any case, those things define something called quaternions, which is a four-dimensional number system with some bizarre properties that multiplication does not commute always, but other very good properties. In fact, this is probably quite familiar in the sense that if we think of the quaternions as the one-dimensional piece spanned by the entity and the complement, which think of it as R3, then the part of the product on the R3 part, which is the most important part, is just the usual vector cross product. So this is a kind of a number system built out of the cross product on R3 and essentially the cross product and the dot product, you might say. So now, we said a Riemann surface is one where multiplication by complex numbers is defined on tangent spaces. A Hyperkähler structure on a four-dimensional manifold is given, well, the main point is that we have a way to multiply tangent vectors by quaternions. So it's a four-dimensional manifold, and we can multiply the tangent vectors by quaternions, or another saying it is that the tangent space is a one-dimensional quaternionic vector space. We should also stick in a Riemannian structure, a way of measuring lengths, which is compatible in an obvious way with this quaternionic structure. But in addition, the whole bunch of stuff is supposed to satisfy a natural equation that the structure is what's called torsion-free, which we won't go into. It essentially just says that it's flat to first order, that it agrees with the flat model to first order in a suitable set of coordinates around any point. But we won't attempt to define that notion more. In any case, these are important things. They can be thought of as one-dimensional quaternionic manifolds in a certain sense, and they satisfy the Riemannian version of Einstein's equation without that cosmological constant. And they're important in theories of quantum gravity, for example, and many other areas of differential geometry, algebraic geometry, and theoretical physics. So believe me that these are very beautiful and important things to consider. The only thing is, starting from the definition, how do we produce any examples? That's not because we can, so in particular, we like examples of what's called closed or compact manifolds. So that's going to be the main, waiting for time, thing we're going to talk about. So I'm going to talk about what's called the Kummer construction. Actually, this would be, what we're going to say would be probably unrecognizable to Kummer, who was a 19th century mathematician working on algebraic geometry, but it's kind of a 20th century point of view on something that Kummer did. So we want to, some more background, thinking about, just generally about ways of making manifolds. So one important way is to start with one manifold and then make another one by identifying points in a suitable way. So I want to give some examples of that. One familiar example is that we start with Rn and identify points which differ by translations by integer vectors. Then we get the n-dimensional torus. This is probably quite familiar. More generally, we can take any lattice in Rn and do the same thing. So what we get is still a torus topologically, but the natural geometry might be different from the the kind of square torus that we wrote down first. Another example we want to talk about is we can take the n-dimensional sphere and identify antipodal points. And then we get a manifold, an important one, called the n-dimensional projective space. And this is a very interesting manifold. For example, the two-dimensional projective space. One can also obtain it topologically by taking a Mobius band and a disk. Those have both got boundary a circle, glue them together along the circle boundary, and that gives another representation of this real projective plane. So that's a picture of a lattice in R2. I mean, that gives you the idea of what the general definition is. At the bottom, there's a picture of identifying antipodal points on the two-sphere. There's a point V, and then the antipodal point is sort of around the back of the picture. So couldn't quite draw it in, but you get the idea. So that's, we've got some interesting manifolds. So now I want to tell you about a remarkable fact of geometry and topology, which is something special to dimension 3. And that's follows. We look at the set of oriented orthonormal frames in R3. So triples of vectors, v1, v2, v3, which are orthonormal and also oriented in a standard way. So this is something we could do in any dimension and get an interesting manifold. And the manifold we get would in general be completely different from any projective space. But it happens in 3 dimensions that this space of frames F could be identified with the projective space P3. And one way to see this uses these quaternions. If we think of R3 as the imaginary quaternions, then we can take our standard frame and move it to any other frame, it's not hard to see, by using a map of the following form using quaternion multiplication. We map a vector v, thought as an imaginary quaternion, to qv q minus 1, where q is a quaternion of unit length in the 3-sphere. If we take minus q in place of q, we don't change the formula because q enters twice. So essentially we can make q to be a point in the projective space, P3. And that construction sets up this identification between the space of frames and the projective space. And it's special to this dimension because the quaternions are special in 4 dimensions. So now, to get on, let's let X be a 4-dimensional manifold given by the set of tangent vectors to the 2-sphere. So this is a simple thing. We can think of a point of X as a pair, v1, v2, of vectors in R3, where v1 has got length 1, it defines a point in the sphere, and v2 is any other vector which is orthogonal to v1. The inner product of v2, the dot product, v2 and v1 is 0. So it's easy to see this is a 4-dimensional manifold. But we can think about it more. There's a special subset, a 2-dimensional sphere sitting inside X, when v2 is 0. Then we just have this unit vector v1. And then the remaining part is actually given by, if we remove S2, the remaining part is just given by taking our set of frames and multiplying by an extra scale factor. Why is that? Because if v2 is not 0, we can always multiply it by a suitable scale factor to make it of unit length. And then if we have a pair of unit vectors, orthogonal, there's a unique third one to make an oriented orthonormal frame. Or if you like, we take the cross product of those two to get the third one. So we've got a description of X as the 2-sphere, sort of sitting in the middle, and then another part which is given by multiplying F, our 3-dimensional manifold, by just a set of positive real numbers given by the length of S2. So now, with all this background and all these manifolds we've learned about, we can explain this Kummer construction. So here it goes. We start off with our 4-dimensional torus. So that's given by taking R4, identify points that differ by a translation by integers. But now we can do something else. We can, on R4, we can take x to minus x, and that induces a corresponding map on the torus. So on the torus, it makes sense to identify points x and minus x to get something else. So that thing is not quite a manifold because there are some special points where x is equal to minus x, and that, as we'll see in a moment, sort of destroys the manifold property. So these just come when thinking in terms of coordinates in R4, our points have either got integer coordinates or half-integer coordinates. Every coordinate is either a half-integer or an integer. Those are just ones which give modulo Z4, x is equal to minus x. So in each direction, coordinate direction, there are two choices, either half-integer or integer, so there are 2 to the 4th, which is 16 special points. And these give points in this space which are not points where it's a manifold. And it's not hard to see that if we cut out small neighborhoods of these bad points, these singular points, then we get a manifold. But now it's got boundary 16 copies of this three-dimensional projective space. So this is a picture that tries to illustrate that in 2 dimensions. So just looking around the origin in the plane, then we're identifying x with minus x. That's the same as taking a half plane and identifying the boundary. So we're just taking a piece of paper and gluing the boundary together in the way indicated by the arrow. And then we get something that's not a the 2-dimensional picture is not an exact representation, but it's obviously got some kind of singular behavior at that special point. And in fact, if you think about what's happening on the boundary of a neighborhood, you're precisely going to construct the projective space in the corresponding dimension one below. So schematically, this is a schematic picture of the 4-dimensional situation. That thing there will be a copy of projective space. So now we're there, we can tell you what this famous K3 manifold is, at least at a topological level. We take our singular thing with the 16 points. I think I actually did 13 probably, but you get the idea. We cut out the singular points. Then we got these boundary copies of P3. But we know something else in which P3 is involved, this thing x. So we take our 16 copies of our x. Again, we represent, away from this 2-sphere, we represent in this product description. We cut off things where the scale is too large for some value, and then we get something again with boundary P3, and we glue the one to the other. We do that 16 times, and then we've got a closed manifold with no boundary. And there it is. That's the famous 4-dimensional manifold. Of course, it's only a schematic picture, but I hope you'll get the idea, roughly, perhaps, of how the construction goes. Well, that's just we're doing for time. That's discussing the manifold at a topological level. What about these Hyperkähler structures? Well, on the manifold we call Y, which comes from taking the torus and identifying points, then cutting out these neighbors of the singular points. There we have a rather obvious Hyperkähler structure, just coming originally from the flat structure on the 4-dimensional space. But more interesting, the manifold X that we wrote down, that also has a Hyperkähler structure, which one can also give explicit formulae for. This was found by different mathematicians independently, Calabi and Iguchi and Hansen, but maybe Iguchi and Hansen perhaps are physicists, perhaps. So that
Hansen is a mathematician.
So anyway, a good collection of mathematicians and physicists have discovered this beautiful structure on this manifold X, this Hyperkähler structure. So we can't quite take the time to write that down exactly, but to give a partial explanation of why this thing should be there, remember X is the tangent space of the 2-sphere. So if you take the tangent space of X, then what you get is essentially the product of 2 copies of the tangent space of the 2-sphere. But the tangent space of the two-sphere is naturally a Riemann surface, so that has its own complex structure. So we can define our quaternion multiplication by the formulae as given, involving, so we're multiplying, so we have bold I multiplying W1, W2. That's given by the ordinary I times W1, where that's the ordinary complex number multiplication, but we use minus I on the other term. And then for J, we also introduce interchanging W1 and 2, and so forth. So these formulae give a way of multiplying pairs of vectors by quaternions. And that's roughly how this structure on X comes about, but it's a bit more subtle than that, because there are certain scale factors that one can choose, and one has to adjust those by solving an ordinary differential equation to get this very special Hyperkähler structure. But that can be done. So what do we finally do to construct our K3 surface is we take 16 small scale parameters, and then we glue scaled copies of X, scaled by these 16 parameters, to Y. And then we use the same kind of argument as we were discussing this bridge principle for minimal surfaces. We're trying to obtain a solution on our whole manifold by gluing together these known solutions. And that will involve first doing doing as best you can by hand, pasting them together, and then using an analysis and differential equation argument to show you can slightly adjust things to exactly solve the nonlinear partial differential equations. So anyway, we'll have time to the outline of how one can produce, one way of producing these Hyperkähler structures. And we can count the parameters in that construction. We could start with a general lattice in R4 rather than the integer lattice I was showing before. That involves 10 parameters when you take account of the fact that we could rotate the lattices and that wouldn't have any effect. And we have our 16 small scale parameters, which are the size of these copies of X. And then the choice of the way we glue in the P3, that also turns out to involve 2 extra parameters in a natural way. You can sort of rotate a copy of X relative to Y. So we get 16 times 2, 32 extra rotation parameters in that way. So overall, we get 58 parameters. What one can show is that in this way, one construct a 58-dimensional space of solutions of this Hyperkähler condition. And in fact, another theorem we proved is that the only closed four manifolds which support these Hyperkähler structures are either the rather obvious boring tori, the flat tori, or this special K3 manifold, M. But this is just the part of the story. I mean, we might think we have this family parameter has got various parameters, but one of the sizes of these copies of X, which you can think of as the size of each copy of X has a two-sphere, so they're the sizes of these two spheres we have. What happens is we try to move away, we increase this parameter. After a bit, we move out of the regime where we can understand them by this kind of gluing construction. So what happens? We get into an unknown regime, inaccessible to this discussion. But in fact, this it's called the Torelli theorem, gives a complete description of all the Hyperkähler structures on this manifold. And that involves the generalization of these periods that we mentioned briefly in the Riemann surface story. So if we have a surface in our Hyperkähler manifold, then we can define 3 functions associated to the I, j, and k. So if we take a pair of orthonormal vectors at a point in the surface, v1 and v2, we take I times v1 dot v2, and that's independent of the choice of v1 and v2. So that gives a function. And similarly for j and k. Then we can integrate these functions over the surface. So for each surface, we have 3 numbers associated to I, j, and k. And these actually depend upon what's called the homology class of the surface. So if we deform the surface slightly, or then we don't change these integrals. So on the K3 manifold, there are turns out 22 independent homology classes. 16 come from the 16 small spheres we had in the copy of X, and 6 come originally from the 4 torus. So if we think of taking those 22 independent surfaces and integrating, say, Fi over those, then we get a vector in R22. And then we do that for J and K, and we get 3 vectors in R22. And we can take the space which they span. So we get a 3-dimensional subspace of R22. So in fact, on this R22, there's an indefinite quadratic form. It's like the Lorentzian forms we talked about briefly at the beginning, but now it's got signature 319. And this 3-dimensional subspace is the property that it's a positive 3-dimensional subspace with respect to this form. Now, the dimension of this set of positive subspaces, as you can see, is 3 times 19, which is 57, which is just one less than the 58 that we found before. And the Torelli theorem, then, what that says is that, in fact, this if we fix the volume, which is just an overall scale, then this positive subspace uniquely determines the Hyperkähler structure, essentially. So there's a one-to-one correspondence between Hyperkähler structures with volume 1 and these positive subspaces. So we get a complete description of all of these things. Actually, that's not. We should really be a bit more precise in a number of directions. One is that statement we want to include some things with conical singularities, like the singularities we saw in the quotient of the 4 torus. And also, we should really take account of the symmetries in the situation. So if we take a map from M to itself, then we can move one Hyperkähler structure to another one just by moving it under this map. We want to consider those as equivalent. So really, we should be a bit more precise in saying what we mean by that. But the point is that there is a complete understanding of these Hyperkähler structures in terms of this period construction. So this relies on, so I say this one, I think this is one of the triumphs of 20th century mathematics. It relies on one of the main ingredients is Yao's solution of what's called the Calabi conjecture, which is, this uses other kinds of PDE techniques to construct solutions of this equation. In fact, Yao originally used what's called the continuity method, but one can also use minimization techniques or flow techniques. But they're different from these kind of gluing techniques that we've talked about before. And they give access to all the solutions, not just the ones that one can understand being built out of these particular simple blocks. But also, this Torelli theorem also relies on many other developments in differential geometry and algebraic geometry over the 20th century. Actually, this has nothing to do with Torelli proved a related kind of theorem involving Riemann surfaces. So since then, all such theorems are called Torelli theorems. This theorem is due to a combination of the work of many people. So this is a great triumph of 20th century mathematics. It gives something one, in a sense, completely understands. But on the other hand, there are many questions about this 57-dimensional space of Hyperkähler structures. And for example, what other kind of different limiting behaviors can occur in families? What other kinds of singularities can develop? And so forth. And this is a very active research area. So finally, 5 minutes to go, we get to part 3. Exceptional holonomy. But that's all right, because, as I said, I want to think about this by analogy with what we've done before, largely, rather than tell you much detail about it. So this depends on this 8-dimensional number system called the Octonions, and there are no more. Technically, R, C, H, and O are the only number systems in the sense of being called technical norm division algebras. And the Octonions can be built again using a cross product, but now on R7, which can be defined by something called the Fano plane. This is a purely combinatorial thing. In fact, it's actually a plane over a finite field, for those who, projective plane over a finite field, for those who know what I mean by that, but it's just given by a set of 7 objects and 7 subsets of those objects, which we call 7 points and 7 lines. And they have the properties as in a plane, that each pair of points lies on a unique line, and so forth. So we use that to define a cross product that EI times EJ is plus or minus EK if the corresponding points lie on a line. Well, there's a bit, I'm not telling you what the plus or minus is, but up to sign, the combinatorics of this thing defines a product on R3, and that gives the Octonions. So then there are 2 special kinds of manifolds. One study related to these Octonions. One occurs in dimensional 8, which is, from a certain point of view, they're one-dimensional octonionic manifolds. Technically, they're what's called torsion-free spin-7 structures. And the other occurs in dimension 7. We have 7-dimensional manifolds with the extra structure of a cross product on tangent space, modeled on the cross product that we've just described. Or technically, these are what are called torsion-free G2 structures. So these are both interesting structures to study. They both give solutions of the Einstein equations. They're important in what's called M theory in theoretical physics. They first arose in mathematics really as part of a general classification theorem of Marcel Berger in the 1950s, studying, roughly speaking, all possible structures that one could sensibly investigate on a manifold. And these are 2 examples emerging from Berger's classification, and there were later important contributions from Jim Simons. But I say this. Well, this is really a 21st century story, or end of 20th century, 21st century. The first, we could ask whether there are any of these things. The first local examples were found in the 1980s by Robert Brandt, who's not quite here. And then Brandt and Salomon found what are called complete examples, where they're analogues of the 4-dimensional Calabi-Iguchi-Hansen thing, X. Then in the next decade, the 1990s, Dominic Joyce found compact examples, first by using an analogue of this Kummer construction in this 8-dimensional world. Then a bit later still, another construction in this 7-dimensional case was found by Alexei Kovalev, which relied on the refined theory of these K3 manifolds that we've talked about. We built up a 7-dimensional manifold by gluing together some things, roughly speaking, along the product of a K3 manifold and a 2-dimensional torus. But so we do know the interesting examples, and in fact, there are millions of examples. There's probably an example for every resident of New York of these things. but very little is known systematically about them. Most. Whereas in the case of 4 dimensions, the K3, we know all about these things, and Riemann surfaces we know in a sense know enormous amount. If we said which 7-dimensional manifolds or 8 manifolds supports these structures, then really no one knows. Once we have one, then again we have a whole moduli space of them, as in the K3 case, and this is related to certain periods, again, that we can write down. But how to describe the whole moduli space, what kind of limits one can get, very little systematically known. It's really studying examples. Similarly, if we have one of these beautiful 7 or 8-dimensional manifolds, then there are various special sort of geometric objects we can study inside it, particular special kinds of submanifolds, calibrated submanifolds, or non-linear generalization of electromagnetism, roughly speaking, called Yang-Mills fields. And then, again, there are particular things that one can do when one has these structures, and many questions that one can ask. But as I said, at present, more questions than answers or complete theory. But we're not deterred. There are many current developments in this area, exciting developments, and so it will surely continue and be many more things discovered as we move on through the 21st century. Thank you.